So first of all, I want to ask you, some of you come to a new area, you want to do a soil quality analysis, what do you do? Examples. Which samples?
Soil?
Yeah, okay. I mean, how do you take them?
It will improve the physical and the chemical qualities.
Physical, chemical, yeah, right. How are you going to take them? With instruments, right? How? I mean, if I want to measure physical and chemical. So what, I take them with an auger?
Cone.
With a cone? With an auger? Right. Okay.
All the type of parameters we are being.
Right, because this is already going to be a big problem for these ones. I think we have to learn to be more systematic, right?
We read.
Sorry?
First we read about
Right. Now I think we start to get here. It's like you don't start cooking and then you just say, okay, I open the fridge. I do cook like that, you know. You open the fridge and you say, let's see if there's something there. But normally you try to do it a bit more organized, yeah, right? So first what you do when you come to a new area is you do a soil, climate, land use evaluation, right? Which is actually called an aggregate evaluation. Because you have to know where you are. If you're standing on the moon, it's not going to be the same as standing on Pluto, right? Because there's a ring around Pluto and there's no ring around the moon, so it's going to make a big difference. So from that, what did we decide? Soil quality. In order to measure soil quality, you need parameters that you're going to measure, right? Now the world is bigger and there is trillions of parameters, so you have to decide which parameters you're going to measure, right? And what did we decide? So you have to come up with a minimum data set. In order to come up with a minimum data set, what were we going to do? We are going to compare the actual land use, so the optimal conditions for the actual land use with the actual conditions. Right? So what's the first step? Read, study. Right? What's the soil classification? What's the climate? It's not going to be the same if you have an irrigated area, if you have a rain-fed area, right? It's not going to be the same if you have an irrigated area where there's a problem with water quality, or if you have an area where the water quality is fine. It's not going to be the same if you're on a steep slope than if you are on a beautiful flat land, right? So depending on where you stand, why? Because we need this, right? In order to know the actual conditions, right? And we need a book to know the optimal conditions. And we compare those two, and from that, you're going to get those parameters that you're going to measure. You measure them all, you do an analysis, and from that comes the minimum data set. And that minimum data set is probably the one that you're going to measure in time. Right? Unless you have unlimited resources. Then you measure everything out there in the world, and you measure it 50 times, so you're sure you have significance, right? But in reality, I don't think that's most of the time the case. You look very skeptical to me. So, not okay? Is it okay? Is it not okay? Yeah, it's still okay? Okay, right. This should be a Picasso which we already talked about, right? I mean, this we already decided. The only thing I'm going to talk about today is how to measure those parameters. Just, there will be probably others, no? I'm not going to cover everything. I'm just going to cover some of them so that you can take them home. Okay. So, soil quality is a working framework, right? Soil quality, if I see the word soil quality, that's obscure, you don't know what it's about. What does it mean, a better quality? Right? It's like sustainability. What does it mean? It depends, right? So what if we use as a concept fitness for use, right? So that we can define what good soil quality is for us. So what are we doing? We're comparing the optimal land use versus the real situation. And in order to do that, we need at least climate and soil classification. I'm really surprised how many times I come to an area where scientists are working, have 4 repetitions, perfectly factorial, randomized complete block design, and if I ask them about the climate, they say, oh, it rains very little. But that's about it, right? And even when you talk about soil, lots of times it's even worse. How can you be working in an area you don't know even where you're standing? So the first thing you have to do is to know what's the climate, what's the soil. And lots of times that's not a lot of work, no? Lots of times it's just going to the library and check it. Maybe in order to do soil classification you have to dig a bit. Look at the profile of the soil and determine which soil it is, right? It's not difficult. So, first one, aggregates. Okay, there's lots of talking and walking about aggregates. Now what are aggregates and what is it actually about? Okay, so we have residue and we have clay, right? What's going to happen, the clay layers are going to orient themselves and going to be stick together by organic matter with the help of microorganisms. Why? Why is clay so important to make the aggregates?
Because it has sticky nature.
Sorry?
Because it has sticky nature.
Because it has sticky nature. Right? There is something about that, but why has it sticky nature? It's a nice way to say it. But come on, that's mineralogy, you know it. Speak out loud. No?
Link the aggregate.
Right, and how does the linking happens? It's there, getting close. How does a clay looks like? If you look at it in the microscope, something like this, no? With molecules here in the middle, right? And it has charges, right? Positive or negative on the outside. How does organic matter look like? That's something like this. And organic matter is plus here, minus there, plus there. So what's going to do? This is going to be the sticky glue that's going to click on the charge here, right? Right or wrong? Yeah? Then start dancing, please. I'm going to hire, like with the TV shows, I'm going to hire somebody in the morning here for the first half an hour to warm the public up so that when I come everything is up and rock and roll. Okay, so you get the formation of the aggregates. Now, during the formation there is CO2 released. Is that logic? Yes, because the microorganisms are eating, are processing the organic matter, making the aggregates, and you get the stabilization process, and then you have the breakdown process. Now, of course, it's a biological influence. Why? You have residue decomposition, you have microbial exudates that are going to help to make the aggregates. You have roots that entangle the aggregates, right? You can imagine yourself a root that it helps to make aggregate. It's going to make a difference between a wheat root and a maize root. Yes, because wheat has a beautiful carpet there on top, while the maize root just goes down, right? You have earthworms and termites. Earthworms, they eat soil and it comes out in the back, but it's processed so it helps to formate the aggregates. Also physical. Dry and wet cycles, drying, wetting, gives physical action and makes aggregates. Freeze and thaw cycles, of course, if you have it, you can imagine below zero, then you release, right? Tillage, when you plow, what do? You destroy basically the aggregates. Root penetration, like I was saying, is going to be different, right? So if you look at it, this is a whole process, and yes, indeed, management is influencing here. If you're tilling, you're pushing this one more to that direction. If you're not tilling, you're keeping them longer there, right? Now, within the macro aggregates, there are micro aggregates. So this is a huge macro aggregate, which was actually photographed under a special microscope. And if you look inside, there is, look here it is, that's basically what I tried to put on the blackboard there, but in reality it looks very similar, right? You see? This is the organic matter. Here is the micro aggregate. So it's a small aggregate within the macro aggregate, right? There are bacteria inside and there are fungi inside. So this is a macro aggregate, and what do we call a macro aggregate? It's everything that's bigger than 250 micrometers. And within that, you have a micro aggregate, and a micro aggregate is everything that is between 53 micrometers and 250. So basically, and I hope this slide appears, no, it's not here. So basically, you have three groups, no? You have bigger than 250 micrometers. You have between 53 and 250, right? And you have smaller than 53 micrometers. This is macro aggregates, micro aggregate, silt, and clay fraction. Right? And this one, and somebody stole my colors, right? And this one, you can further split up in micro aggregates within the macro aggregates, right? And silt and clay in the macro aggregates. Do you agree? Yeah? So, first, we split out these, and then we split out these. So we just take the same fraction, and we split them out again, right? This is all based on the theory described by Six et al. 2002, but I do recommend you that you read actually, that you go up and you go to the more recent papers, because there has been some changes in Six et al.'s theoretical framework of aggregation, right? Especially about the microaggregate formation and how microaggregates are within microaggregates. Now, how microaggregates are within the microaggregates. Now, right, this is a beautiful system. It's not difficult, there are instruments out there, I'm going to show you how to do it. But still, it's not about going everywhere, taking soil and starting to measure micro macroaggregates and then split them open. It's beautiful, I mean, you know something and then you just apply it everywhere. That's not the right thing to do, right? We have to know why are we measuring it? What do we want to simulate? What are we looking at, right? So, if we are looking at infiltration, stability of the soil to infiltrate, what we are going to do then is basically only split these out, right? We take the soil and we put them in water. Why do we put them in water? Because basically, when you have a macro aggregate, and it rains a lot, so it's standing in the water, there will be pressure from inside because there's air trapped within the macro aggregate, right? If that air trapped within the macro aggregate is stronger than the ties that keep it together, this one will disintegrate, right? And what will happen is you will have crust formation. That's exactly what you see in the field when you have plowed, you have a heavy rain shower, and the whole topsoil seals, right? So So if it's that process that you want to be quantifying, then it's enough to stop here. Why would you go further? This is related to infiltration, to topsoil structure, right? The whole thingy about microaggregates within the macroaggregates, that is when we are talking about carbon sequestration. Because the theory says, if your carbon is within a microaggregate and that microaggregate is within a macroaggregate, which is stable, and it is protected. It's like putting it in a plastic box, right? It's like putting it in a Tupperware, something like that. So if you want to go more to C and N cycling, then you do measure this, right? So what I want to say is, you don't measure something for the sake of measuring. You have to think about what is it I actually want to measure. Which question I do want to answer. What is the question I want to answer? If the question is carbon protected better in this system than in the other system, you go to macroaggregates within the microaggregates within the macroaggregates. If your question is, I want to see the structure of the topsoil, is there topsoil slaking because I want to relate it to infiltration, then you just go to this. So the microaggregate formation within the macroaggregates. Through microbial processes occurring within the stable aggregates, you get microaggregates within the macroaggregates, right? And some of them are earthworm casts, right? So you can imagine that macroaggregate formation is favored in zero-till systems, and that the inclusion of microaggregates within the macroaggregates is favored also. Now, first methodology that was developed is dry sieving. Dry sieving, you have a machine, you put a set of sieves on top of it, you drop the soil in, and the soil is divided over the sieves. So basically what you have is a disruptive spores, a nest of sieves, you shake it, and then you determine the weight of the refraction, and you can calculate the mean y diameter or the fractal dimension. Why? Because of course, if you have 8 sieves here, you're going to have 8 numbers. So you have to summarize them in one number, because otherwise it's very difficult to work with it. So that's why we are calculating the mean wide diameter. Right? I will explain you how to calculate that later. Now, what does this tell you? Is this aggregate stability? Is this aggregate stability?
No.
No. This is aggregate distribution. Right? This is not related to topsoil slaking. Because topsoil slaking is related to the water force, right? The only thing that this is going to do is telling you the distribution of the soil. What we see lots of times is when you do dry sieving with conventional tillage and with zero tillage, it's more or less the same. But when you go to wet sieving, you put the soil into water. The one from the zero till with residue keeps stable, but the one from the conventional falls apart. Okay? Why? Because the structure is okay in conventional till, the distribution is okay, that's why you till, but the stability is not okay. Okay? So wet sieving is aggregate stability. Dry sieving, aggregate distribution. Wet sieving, aggregate stability. So one of you read the paper, Limon et al. 2002 Soil and Tillage Research, where it was only done dry sieving. Who was it? I don't remember. You remember I made a kind of a remark and I said we would come back to this? Because it was only dry sieving and it was not wet sieving, while in the next paper from Limon et al. 2006, there was actually, then it was changed and it was, wet sieving was included. Right? And in that follow-up paper, you see exactly the same. Permanent beds with residue have good distribution and good stability. And conventional beds with residue have good distribution but bad stability. And permanent beds burn have bad distribution and bad stability. So what do? You have the soil, you basically slake it, nest of sieve, you move it up and down, you put every sieve in a plate, you put the plates in the oven, you weigh the plates, and then you still have to do sand correction. So on all those plates, you disrupt, etc., etc. I will explain you in the lab. Now if you do this, it's better to do it over the weekend so you have the lab for your own, okay? Because you're going to produce lots of plates and lots of space in the oven, right? But it's a beautiful thing to do. I really like it. The other methodology is if you have less, is doing just by hand. Big sieve, which sieves are it going to be? 250 micrometer sieve, of course. 53 sieve, so you put the soil first through this sieve. What goes through this sieve goes to this sieve. What stays on top of the sieve is this fraction, what goes through it is that fraction, right? Problem with this methodology, you can see it already, lots of water. So you need big buckets, right? Now why am I showing this? I'm showing you this because I want to tell you a story. When I came here for the first time, there was nothing about soil. There was only a chemical soil lab. And it was there because they have a plant lab. And they said, well, if we have a plant lab, we can equally call it a plant and soil lab. I mean, it sounds a bit more fancy because we have already bought everything for the plant. So let's do it for the soil also. So for the soil, it was easy. For the chemicals, it was easy. You just took the sample, you put it in a bag, and you send it to the lab, and the results come back. But for the physical, there was nothing, right? There was nothing, and there was no money. This one, you can perfectly do, right? You call the local university and you ask for 3 sieves. That's about it. Same thing we did in Ethiopia. We had 3 sieves, that's about the only thing you need, and a drying oven. The rest you just invent. What did I do? I just asked the local bakery factory to give me some of those, because these are the plates you use to make cookies, no? For bakery, and you can, if you need the big ones, you just ask the one they use to make pizza, or to make the ones for the big cake. And that's the only thing you need, and you can perfectly work. What I just want to say, there is no money is not an answer, right?
That's good imagination.
You have to use the brain. Same thing here. If you buy this new from Ekelkamp, you all know probably Ekelkamp, it's that big Dutch company where they only work from 9 to 5, so if you're living in Mexico, that's a problem. But they sell fancy things, right? Sometimes it's okay, but this one we just made it with a local blacksmith. The only very expensive thing is here the motor, none of this inside. This one, of course, we made ourselves. The most expensive thing here are the sieves. Those you have to buy from Ekelkamp or from another provider, right? But my dry sieving, you can see it, my dry sieving instrument is much less fancy than the one you have in the lab in Ethiopia that was bought with the big money. No? Okay, for the isolation of the stable aggregates, like I said, we have to disrupt the macro aggregates to get the micro aggregates that are within the macro aggregates. Now to do that, we have this device, right? Now that device is a special device that was designed by UC Davis, by the team of Yard 6. So this is more fancy. It is also made just out of plastic tubes, and just you put it on a shaker and it will work, but you do need the design to make it. Okay? But like I said, you don't always need to go to that step of micro aggregates and macro aggregates. Another thing is also you can already do a lot with your eye, right? Because the soil structure morphology is different. This is a good structure morphology. This is pure, right? And this is in between. If you're a plant, you are happy to go here, no? Because you can go with your roots wherever you want. If you're a plant here, you have to already separate. Not to tell that if you're a seed and you're sitting here, man, it's tough to get above the ground, right? While if you're sitting here, well, you can just follow the light and you get out more or less okay. Same thing. First thing you can do is dig a pit. Make a pit and look at the soil morphology. And you're going to see already big differences. We will do it out in the field today. Now, infiltration. If I was shown in my university, if you measure infiltration, you have to measure double ring infiltration. Where does the double ring infiltration come from? It's a methodology developed by the FAO in order to do irrigation predictions, in order to determine how much water you have to apply on irrigation, and it's developed for conventional tools. I came here and I tried it out. This is the proof. I had no double ring, so what we did was here in front, I don't know if you've seen it, but here in front there is an old metal collector, so somebody that collects all the garbage from the metal, and we just went there and we asked them, we cut the tubes. And we had a beautiful double ring. Problem with the double rings is zero till without residue. You have a crust. Now you're going to put the double rings there, and of course you have to get them in the ground. Because the double rings, you can see, they have to be like 15 centimeters into the ground. So, if you are fancy, you buy a kind of a pressure plate and you pressure it into the ground. If you're not fancy, you just drill them into the ground. But in the both circumstances, what happens, the soil crust just breaks open, right? You have never moved the soil, but when you put the double rings in there, all of a sudden, the soil breaks open. So then you imagine you put water on that, it is gonna go in very, very quick, right? So the double rings are okay, but they are difficult to use in practice, right? And what they also give you, they give you saturated infiltration. That's why you have a double ring. You have a double ring because you want this, you're measuring this flow. And you're putting water here in the second ring, well, between the first and the second ring, because you want to wet this front, because you want to avoid that this water is running that way, right? That's why you do it with a double ring. So that you have the saturated infiltration rate downwards. That's okay. But it's maybe a value at one, it's difficult to measure, and second, for zero till, it's not only always really reflecting what we want, right? So that's why we went to a methodology that is actually a rainfall simulator. But like I said, when I came here, there was no rainfall simulator. So we built a rainfall simulator. And actually our rainfall simulator is just, look carefully here, an arrow sitting on the ground. And we went to the local market, and this one costs $2, right? And it just took me half a day to calibrate my arm so that I'm watering the same every plot. And what I'll be measuring, we water in the middle of the plot, and as soon as the water runs out of the arrow, we stop. And we call it time to plant. Now what's the funny thing about this? With this one, you can go to a farmer. Go to farmer fields, and you can show him actually the difference between the different fields. Right? Now, of course, this principle, you can make it much more fancy. You can go for a real rainfall simulator with, so the wind is not blowing. So, yeah, of course, and the more precise, the better. But you have to be able to walk on that scale of, okay, I have lots of money, so I buy the most fancy equipment. If I have no money, I want easy and quick and dirty. This is quick and dirty, I agree. But still, with this one, we got very significant results between different treatments. And this is actually reflecting what happens when there's rainfall. Here what happens when it rains. Right? Other thing we do is one ring infiltration. And if you measure then moisture, etc., you can calculate from that saturation infiltration. There are other methodologies. You can dig a hole, pour water into it, and see how quick the water is disappearing in the hole, right? So there are lots of methodologies to measure infiltration. You look them up, you do literature search, right? But what I want to say is, my objective was to come up with easy and quick tools that tell you something about rain-fed agriculture. So this one we used in Ethiopia, and it gave good results. Impact chronometer. We built it ourselves. Based on this design, you just So it's just a weight, you drop it, a weight, you drop it, a weight, you drop it, and you go recording it. And then you can turn this with the formula into the resistance of the soil. I know there are those fancy ones where you just drill them into the ground and you have a computer on top of it and the computer just registers and then you pull it out and you get a graph. But also the computer is only giving you a value every centimeter. There's another one where you pull it in and there comes and you push and there's a kind of a card, a paper that flies out of it, and then on the paper with a pen there is a profile, right? Yeah, it's true, but this one is the cheapest one and you can make it yourself. And it works perfect. And there is actually a paper that is comparing different penetrometers and this one came out as the most reliable one. Right? Now, there's another story. I once got a fancy one and I was measuring in the field and I was measuring during a whole day and it was 4 o'clock and I came to it was not the last plots, there were still 3 plots to go. So I came to I said, yeah, we are already there, we are almost there. I pushed the penetrometer and I pulled it out and all of a sudden the battery went flat. So I lost all the data of the whole day. So that's when I decided next time we're going to do it like this and I'm just write down the data and then I'm sure at least that I have it. So I say you have more fancy ones. Now this is a cone penetrometer. What's the history of the cone penetrometer? Now cone penetrometer is one where we really use to only measure the topsoil. To just push the cone into the soil, right? This is actually developed by the American Army. How funny it may be. Why? Because they were coming with their big tanks and all of a sudden they had to pass a muddy area. So they didn't want to get stuck with a big truck. Let's say a big truck full of munition. They wanted to get stuck in the middle of the mud. So designed this one and what they then did was you send somebody in front to measure the resistance so that a truck can pass. Right? That's the history of that one. So that's for topsoil. Now a more fancy thing, for example, and yes I have that system, this is something that's recording the soil temperature. Soil temperature, because you said it's an important parameter, so that's why I put it in. So these are, you just put them in the ground, there's a small, here's a small box around it, and that records. Now, why do I say this? Now this one is actually only for use within the lab. If you want the ones you have to use outside, right, then you have to buy much more fancy ones. You have to buy, and they cost 4 times as much as these ones. Now I do use these ones outside, because what I do, it cannot get wet. So the only thing I did is, I made a plastic box, I drilled 4 holes in it so the cables can get through it. I put the paper inside, I close the box, I put the paper around it, and I put the plastic back around it. So if the water goes in, it's first the plastic bag. Then if the water goes in, it is absorbed by the paper bag that's around, because the paper grabs the moist. Then if it still goes to the plastic, there is still a paper in there, so the paper will first grab the moist. So it works perfectly, and I saved several $1 million, well, several $1,000, right? So it's about using your head. Now, soil temperature, of course, you can also measure it with very cheap $2 thermometers. The only thing is that then you have to walk every day your fields and just record at the same time, same hour. CO2 measurements. This is a CO2 measurement flux meter. This is more expensive, and there is no cheap way to measure CO2 flux. Now there are even more fancy ones. What we are going to see in the field today also is we now have chambers that were designed by a student of mine. I didn't do it. A student, Leonardo Coutinho, he's from Staff, and same thing, he designed the chambers himself. We let them make by in a local shop, and what we do there is we just extract with a needle, we extract the air, and that we analyze for trace gases in a chromatograph. Right? This, of course, you know, soil bulk density, soil moisture, just by gravimetric and with the soil density. With the bulk density, so you can turn it into volumetric. Now, bulk density, we're going going to see how you can do it with a ring, right? Most of the soils that is okay. There's one soil that's giving you a headache, that's a vertisol, right? Because it's well shrink, so you never know when should I take the bone density and how should I take it, because when you drill the ring in, you're compacting that soil, so that's a very difficult one to actually get real values of the bone density. Root rot. Now Monica is going to tell you more about that on Friday, but again, it doesn't have to cost much. The only thing we do is we pull out the plant, we watch the roots, and we look at them, and we score them. Completely free, if you have time. On the relative scale. Same thing, insect damage. I pull out the root, I wash the root, and I go looking for carves by insects, and I make a scale on which to rate them. Same thing for wheat, root rot, right? Put it on the magnifier lamp, and that's it. Now, for example, one detail. Why is this? When you do it, you put a bucket of water. Now put a white bucket of water, right? Because that's going to reflect, so you're going to be able to see much more the contrast of the brown root rot. If you put a red bucket of water, it's going to be much more difficult to look at the roots, because the red is not going to reflect that beautifully and not contrast that beautifully with your roots. Details, but think about it. Like I said, insect damage. You can see here, this is a brown root, it's eaten by insects. This is a 7. You see, this is a 4, this is a 7. You can easily do it yourself. Just pull out the plant, wash off the mud, and just look at it. Right? Then headlight, same thing, just go to the field and score it. Now you know, it sounds easy, but it takes a bit of time, because you have to count every... And then you can, but it works, right? Same thing for leaf blight. Go and look to the area. So now, the thing I want to tell you here is, when you see something happening in the fields, you try to quantify it. And if you're rich, you immediately call an American company and you say, send me a satellite picture, or send me an instrument to measure the light reflectance. Send me the NDVI. If you're not rich, you find another way to do it. But still, score it. Try to quantify it. Get the maximum of data out of it. You have only one chance, because tomorrow it's already another day. That's the only problem with agronomy research, right? That you can never sleep, you can never stop, because the plant's not going to wait for you. So, now the question is what it is in real life. So what we're going to do right now is we're going to go to the fields and the lab, and we're going to show you how to do it in the reality.